Closing talk of the day. It is a pleasure to welcome Michel Bergh, who will be talking about exceptional sequences on Fano 3 folds.
Okay. Yeah, maybe to tell you how I know Karen. We were both together in 1995 at MIT, I think.
That's right.
I was a visitor and we were postdoc. And we were both interested for different reasons in differential operators. So it was natural to go.
Can you speak louder, please?
Oh, is there? Oh, there's no
No,
microphone.
the microphone is there,
Where?
on the floor, on the floor.
Yeah, that's on
That
the floor.
That black thing on the floor.
Michel, right in front of you. That.
Oh, so I should. Okay.
Stand
to that.
It's not something that you click on.
Oh,
Okay. Yeah, so today I'm afraid we'll be less close to what you worked on, but except that it will be about algebraic geometry, so and there's some. Okay, so the title's been set, so it's about exceptional sequences from Fano folds. So it's about joint work with my graduate student, who's about to finish, Anja Notskova. And the ground fields will be most of the time the complex numbers. So, so let's start with a triangulated category. And I mean, it will be enhanced. I won't say what that means if you know it. So it means that you can do the homological algebra is a bit more flexible than you could normally do in a triangulated category. So inside A, we can define the set of full exceptional sequences in A. So there's some words here. So it's about sequences. So the elements of that set are sequences. And there's the length of the sequence is kind of a hidden parameter. I mean, they will all have the same length. So I don't write it. So this is the, then I'm not sure. So then what's exceptional? This means that the objects have no non-trivial x except the hom, which is k. So this would be exceptional. The fullness is a generation property. So the fullness is that A is generated in a suitable sense by the elements of the sequence. And then there's one important condition I forgot to mention. In this sequence, there will be no backwards x. Okay. So there's many reasons why people look at these. One of them, if we take the homomorphisms then I should take the derived endomorphisms. So this will be the G algebra, but it's often just an algebra. Then and I forgot to say, the category needs to be non-finite. Otherwise, the theory doesn't make sense. So this is usually some small algebra, so it gives a small data to describe triangulated category, and then just to give one example, if you take Pn, then so we take A to be the derived category of coherent sheaves on Pn. And then, yeah, in that case, lambda is very easy to describe with a simple figure. Now, the point is, if you have one exceptional sequence, you immediately have many. So this is the subject of mutations. So we have a great group action on the set of exceptional collect, I should say here, because of isomorphism, on the set of equivalences. And how does it work? So the braid group are standard generators. And so we only have to say how the generator acts. So sigma I. So the only place where something happens is at EI and EI plus 1. So where so this is the code. I mean, you know, conormal is not a functor. That's why you need the enhancement or to make this into a functor. Now there's a very old conjecture. I assume from the 90s by Hondal and Bonichuk, which says that the brain group and then semi-direct product with some free group acts transitively. Okay, so this thing is given by the shifts. Because if I have an exceptional, a full exceptional sequence, I can shift the individual parts, and this does not. This is still a full exceptional sequence. Now, it's recently been shown that this conjecture is actually false by item. And scroll. So in 2023. But the counterexample is kind of non-algebraic. So it's Fukaya category. A topological. Fukaya category. On its surface. So I'm not going to define this. Fukaya categories, they come from mirror symmetry, and in general, they require very hard analysis to define them properly. But on surfaces, this has been completely simplified, and there is now a quite easy algebraic definition which one can use. Okay, so what about the algebraic case? So what about so I'm going to shorten where X is a smooth projective variety. And then there's some cases where it's known to be true. True for Fano two-folds. So also known as delta surfaces. So and then the other ones are given by blow-up of E2. Blow-ups. And then it's also true for the second. This is originally Rudakov, who did P2 and P1 cross P1, and then Kuleshov and Orlov. Who did all delta Zeus. And then the second Hertzberg surface so this is a there's also so this has relatively recently by Akira Okawa and Jahaya. Okay, so that is very much open in general. So so then I can I will now state the theorem we can prove. So so this will be about three-folds. I'm going to give a strange list. So this is projected space. This is not strange. Then Q3, I'll define this is quadratic. Then V5, and V22. So these are symbols in the classification of Fano three-folds. And I'll tell you why precisely these. Actually, so this is not part of the conjecture, because in general you don't have freeness, only transitivity, but in this case you get something stronger. So it acts freely and transitively. Um, and this result isn't totally new in the sense that Polachuk proved a version of this result for exceptional collections of vector methods. Exceptional sequences. Okay, so what is this list here? So what's special? So there are many characterizations of star on this list. We give a few in our paper, but there are more. So that's sort of the simplest, from a suitable, in a suitable sense, found on threefolds. So one characterization is with exceptional collection of its full, with a full exceptional sequence of vector bundles of length 4. So let me sketch a construction of P3. I think no need. So this is a quadric in P3, and then V5 is a linear section of the Grassmannian 2-5 embedded in P9 in the quarter embedding. And then V22, these are the zeros of 3 sections of so this U is the universal subbundle. So here, the exceptional collection, we've already seen it. And this is constructed by Landau and Bergh and Son. Here, an exceptional collection was constructed by Catrano. And here by Orloff. And here by Christensen. So, in the rest of the talk, I will have to refer to these exceptional these exceptional sequences, even though I haven't actually written down what they are. So I will write them as with a superindex, where S means so like this is kind of the standard exceptional sequence, full exceptional sequence on P3, and there are similar, more complicated ones on the other on the threefolds. Okay, how do we approach this? And we basically follow a relatively standard approach to start, which college should also did. So approach. So we take the zero set of a generic section of minus one canonical bundle, and it's known that this is a K3 surface. So this means that Y has trivial canonical bundle, and it's not an abelian surface, so it's, the additional condition is that it's simply connected. And how do we relate so what's the relation? So fact that if we have an exceptional object, then if we pull it back, so this is contained in X, and let me probably include in Y, then this is a so-called spherical object. So spherical means if this so this is kind of the smallest possible X groups you can have on a surface with this property. So, okay. So now I'm going to talk a little bit about K3s, so forgetting the motivation. So let Y be an arbitrary K3 surface. Except I'm going to assume that, so this holds here, the rank of the Picard group of Y. So this, so this is sort of the generic case. If we have a K3, then we can always deform it such that this holds. So this means that the Picard group has a single generator, and I can always assume that the generator is actually ample, and we can use it to define a degree of a K3 surface, which is the self-intersection of H, and it's always an even number, so I write it as 2 delta. And I will make another assumption. I assume that D is at least 4. So for the theory is slightly different for D equal to 2. So just ignore this because it will not be relevant in this context. Okay. So it's a well-known principle that kind of omega y, because it's kind of can be categorically defined more or less, obstructs the existence of autoequivalences of the derived category. So if we have this, then the obstructions are fewest in number. So we kind of expect this to be a fairly large group. And actually this group is known. Well, a lot of it is known. I can say that it's known. And this is so the story is basically that Richland started this, and then this paper by Bayer Richland is sort of the final result. But there are a bunch of other people that also contributed, and I will give the names later. Now, this group contains an interesting subgroup, which is the group generated by spherical twists. Okay, spherical twists are associated to a spherical object. So let me write the set of spherical objects always up to isomorphism. So if we have a spherical object, then we can define something ts which acts on objects like so in this it's a famous result by Seidel and Thomas. That ts is an autoequivalence. So I will call this group G, so just some random symbol. So it's kind of an interesting subgroup of the derived total equivalences. And our second theorem, so yeah, what I had before was theorem 1, this is theorem 2. Also by so first of all, he is freely generated by for some set and it's this set may be infinite. So this group is not free, generally not free, and is finitely generated. This group is always free, but cannot be finitely generated. And then 2.
So it's true for any K3 surface?
Sorry?
It's true for any K3 surfaces or K3 surfaces of Picard random? What's the context? Yeah. So is it true for any K3 surfaces?
Well, rank
Picard random.
Picard rank 1.
Okay.
Yeah. So everything I say is about Picard rank 1. If I say something is known, then it's for Picard rank 1. Right? And then 2, something a bit more technical to write. If I have a spherical object, then I can sort of build it from these SIs. Or so the epsilon i's are signs, and then so I can build every spherical object from this set. So I will use an ad hoc terminology. I say that we say that is a basis for more accurately, one could say that one can make this into something like that's called a quangle, and these could be then free generators for the free quangle. Some corollary of this, which actually is the thing I want to use. A note. So if I call this part H, so H is an element of G, and it follows from the properties of spherical twists. In other words, this is in the conjugacy class. Of one of the basis elements. So I give an idea of the proof. So first of all, we have the extended neuron symmetric group. So these are both Z, and this by our assumption in the garden. So this is a Z cube, and this should be viewed as sitting inside the homology. And then there is a twisted intersection form. So this is an element of Z3, which we have identified with N. So this is and then if we have a quadratic form, we can make a bilinear form. Um, and Okay, why did we do this? I'll assume that then there's something called the Mukai vector. Introduced by Mukai, of course. And I'm just going to write the formula. We don't actually need the formula, but just this is an element of the extended neuron severity group. So the observation is that so this is minus so in particular if I have a spherical object, then and I take its Mukai vector and I evaluate the quadratic form, but it's -1. The reason it's -1 and not -2 is that. So in other words, so Vs is a root Q. And so that into the following definition, so this is the set of, we call this a set of positive roots. And the result from combining some results of these people says that for all positive roots, there exists a unique hecadungle S rule so there will be many spherical objects with Mukai vector rule, but there is a unique one which is actually a vector bundle. And then okay, now we come to the theorem, which appears in a paper by Bergh and Richland, but it incorporates results by U rates. Marquis, Stellahari, and also Kalatani. It says that there is an exact sequence of the following one. So, this thing is grouped by generated by this squares of the spherical twists precisely for these S rows corresponding to positive roots. And shift by 2. Okay, this would take quite a bit of work to define formally. So this is a lattice of rank 24, but it has a Hodge structure and a bilinear form. So this is the Hodge, and I'm not going to define this, just write it down. Hodge automorphisms. The positive foreplane, the orientation. Of positive. So this has signature 420. So that's the 4, and then this has an invariant. This has a quadratic form, and you look at the 4 planes to which the quadratic form restricts us on the positive definite. And there are 2 connected components, and we want the connected components to be preserved. Now this, looks pretty horrible because it says rank 24, but the Hodge structure really cuts it down a lot. So this group is not so big as you would expect. So as I said, this is this is proved using moduli spaces of stability conditions. So associated there's a stability manifold, and I'm not going to define it, but this is a complex manifold. So this theory was created by Michel. So this means that the derived outer equivalents of dy, they act on on this complex manifold, but in particular on this topological space. And somehow this this sequence is derived from this. Now, I'm going to sort of give a. One can make this sort of more concrete, so I'll make this more concrete. So can be made concrete, very concrete. So let's introduce hyperbolic plane with a complex upper half plane. So this is equipped with a hyperbolic metric, and it has an action PGL2. A, B, C, D acts non-Mobius transformations. And inside here, we have a subgroup, which is called the Frege group. So it's defined by taking the standard congruence subgroup so this is usually denoted by gamma 0 delta. And we adjoin one more element. So this is one of the standard modular standard congruence groups. So so this acts discretely. So if we have a root, then we define and then we let so we remove from the upper half plane a discrete set of points. So then we have a hypersequence. So this is a stack actually, so it's an orbifold Riemann surface. So then we get sort of a standard exact sequence for fundamental groups. And this is discrete. And here we have that delta. So normally you would have pi 0 and delta here, but since it's discrete. So this turns out to be won't be able to do everything I wanted, but okay. So this is something we rediscovered, but then hardly still does that. This was in a recent paper by Fano. Okay, now inside here, we can find G, and then we can take the image here. So this is, recall, this is generated by spherical reflections, and this group is generated by point reflections. At the positive roots. So in the Euclidean plane, a point reflection, since that only uses the metric, you can also define it in the hyperbolic plane. Well, one more minute. Maybe two, because then at least I can say why I did all this. So the analog of this says that G acts freely. Because basically we removed all the points where it doesn't act freely, right? So in other words, the quotient is actually a regular topological quotient. And I can show that this is contractible. This is not immediate, it requires proof. But then by the uniformization theorem, it implies that this is a disk. So this is a disk minus a countable set of points. So its fundamental group is free. So that sort of gives part of the theorem too. Now, 1 minute, how do we go back from the K3 to the Fano? So assume now that X we have a generic K3. Then we have the set of exceptional collections, full exceptional collections on X, and it has a great group action. But then we can send to the restrictions on the K3. So this lands in G4. And the point is that there's an action of a great group that intertwines this, and this is a so-called Hurwitz action. So if G is any group, then we have a great group action, and this says that sigma I So in the fact that this is a lot is known about the Hurwitz action on free groups. So then we can use this and then pull it back to that side. That was it.
Questions? Okay, just want to make sure I understand it correctly. So, did you say that the orthodox conjecture is not known for Pn? That
No, P3 is, no, it's not known from enough for Harvard. Yeah, it's very little is known actually.
other questions?
Okay, let's thank Michel again.